All right. Whatever I said before. Okay, so remember. Okay, so like if I write out a chemical reaction, those reactions don't tell us anything about the reaction. Don't tell us temperature. Don't tell us whether those reactions are. We're assuming they're spontaneous, but a lot of the reactions that we're looking at don't happen spontaneously, right? If I have butane or methane or methanol just in the room, they're not automatically going to react with oxygen in the room. There has to be some sort of input energy that's going to make the reactants react. And so part of that is collision reaction theory, which you would have talked a little bit about in Chem 20, right? We assume that in a compound, the molecules are constantly moving. And so they are in constant random motion, rebounding elastically from collisions with each other. Elastically. Got it. Right, so constant, rapid, random motion, they're hitting each other, they're hitting the walls, and we assume that in these collisions, none of the energy from them running into each other is being lost. Even though we know that's happening, for our purposes, we're going to assume that that energy is maintained. A chemical reaction must always involve the collision of reactants. So, methane and oxygen have to collide in order for a reaction to happen. And during that collision, we have to have sufficient energy in order for the reaction to occur. Right? Like I said, methane and oxygen, they're not going to automatically just combust together. There has to be some sort of sufficient energy for that reaction to progress. And lastly, the part of this collision reactant theory is not only must they be like hitting each other, they have to have the correct orientation in order for the reaction to happen, for the bonds to break and then reform. And so those are all parts of the collision reaction theory. Constant rapid bound motion, elastic collisions. We have to have a collision between our reactants with sufficient energy and the correct orientation. Right? Sufficient, oops, sorry. It's the big parts here. Sufficient energy and correct orientation. That has to happen in order for our reactions to occur. Everybody's okay? Okay. Lovely little diagram. Inefficient collision, effective collision. So if there's not a sufficient energy, the reactants would just stay as they were. All right, and so what we need to realize is that, again, like lots of things don't automatically react. We have to have some sort of initial energy for the reaction to occur. And so what that's called is activation energy. And that's the energy barrier that must be overcome for a chemical reaction to occur. So the energy barrier that must be overcome for the chemical reaction to occur. And this energy could be input in by a whole bunch of different ways, right? Maybe we add heat to it. Maybe we stir it, and that's enough for the reaction to occur. Maybe we have to add light. Sometimes light acts as a catalyst, helps the reaction occur. Sometimes we might add electricity, whatever it is, in order to make the reaction occur. And that gets us over that activation energy. And so if you were here yesterday, I got you to do the card sort. And so before, when we're looking at potential energy diagrams, I was saying, here's the products, here's the reactants, the reactants, here's the products. First of all, exothermic or endothermic reaction? Exothermic, right. But if you were here yesterday and you've seen the diagrams, really what these look like is like this, right? When we are writing our potential energy diagrams, we're not taking this initial or that activation energy into account. But we need to realize that that is actually happening. And so there's going to be energy required in this area. Enough energy needs to be added to the system to essentially break apart the molecules and then recombine into my product. All right, and so the top right here, that represents our changeover point. At that point, we have what's called an activated complex. In both endothermic and exothermic molecules of the reactants are moving with a certain amount of kinetic energy. Yeah, it's not that important. It's essentially just saying in this portion of the graph right here. So in this portion of the graph, I guess more like this portion of the graph right here, the molecules are just moving with kinetic energy, and then we have a change in potential energy, especially at the top, and then that would kind of either go lower or extremely low, depending on what the products are going to be. And so at the top there, where I put the star on the diagram, that's what's called an activated complex. It's like an intermediate step when essentially all of the molecules are broken apart and they're about to recombine. That's what our activated complex is. It's also that very top point on our potential energy graph. And it's like a transition species that really doesn't exist. We don't account for it in our chemical reactions, but it is there. And so just to kind of look at where this would be on these graphs, so at the very top, regardless of what you're looking at, is going to be your activated complex. Okay, question, what's the purpose of a catalyst? You look at catalysts in biology, what's the purpose of it? Speed up a reaction, okay. Right, yeah, exactly. And so a catalyst essentially is decreasing the amount of activation energy that's required for something to happen, or for a reaction to happen. So catalysts are a substance that are usually there in small amounts, and they modify and increase the rate of the reaction without being consumed in the process. And so sometimes just light adds as a catalyst. Light can add enough energy to make a reaction occur. Sometimes actual catalysts are needed, like in your body you have enzymes, which are catalysts that help reactions occur. They're not used, they just decrease the amount of energy and help the products being formed, and as well, usually quicker. Alright, and so catalysts are essentially providing an alternate pathway in terms of energy requirements for the chemical reaction to occur. And so catalysts lower the activation energy, and as a result, they're usually going to produce a greater yield in a given length of time. So if I had a reaction occurring in 10 minutes without a catalyst, I should get way more if I have the same reaction occurring with a catalyst. Eventually, the uncatalyzed reaction would hopefully get there, assuming that we had enough potential or kinetic energy for that reaction to progress. Alright. Sorry, did everybody get all that? Sorry. And then so there's just an example of the different pathways. So the black here would be an uncatalyzed reaction, and the red is a catalyzed reaction. It just lowers the activation energy for that to occur. Okay, test question. A correct statement about the reaction represented by the enthalpy diagram above is it exothermic and would require energy to start it? Is it exothermic and would not require energy? Is it endothermic and would require enthalpy to start, or endothermic and would require more than the reaction enthalpy to start it? Exothermic or endothermic? Endothermic, right? I'm moving up, so it's not either one of these guys. And so they would require the reaction enthalpy to start, or would they require more than the reaction enthalpy to start? Does anybody know? More, right. And so remember, enthalpy is strictly the difference in the energy between the products and the reactants. So this right here is the enthalpy of that reaction. And so for this reaction to occur, I need way more energy than just the enthalpy in order for that reaction to occur. I usually don't just jump straight up, even though in terms of the diagrams we've been looking at thus far, they do that. That's not really what happens. So that gives us with the answer. Yeah, I know. I was wrong. Okay, bond energy. I don't know how much we need to write here. What? I know, but now we're talking about the amount of energy, like, so in an exothermic reaction, we're looking at talking about what has more energy. Like, does it take more energy to break the bonds, or does it take more energy to make the bonds in terms of endothermic or exothermic? That's what we're looking at now. And so, yeah, we already know all this about exothermic, endothermic. Doesn't mean that you won't get it wrong on the test, right, Travis? Yeah. Wrong? I don't know. He just seems like he's like spaced out in the back. Oh, I didn't even see the pencil. Now I see the pencil in your hand. So. No, he just had like his head up like back there and couldn't even see his pencil. All right, so exothermic, we release energy, and so energy of breaking of the bonds in an exothermic reaction releases energy. And generally that means that the reactants have more energy than the products. My delta H is what? Negative. And if it's in the chemical reaction, is it a reactant or product? Product, right. All right, so endothermic reactions, again, you already know this. Endothermic reactions have to absorb energy, and so the making of bonds, or like the making of substances in an endothermic reaction is going to require energy, more energy in there when we're creating the bonds. All right, and so the stronger the bond, the greater the energy required, which really relates to yesterday when we were looking at the heats of formation. If you have a very negative heat of formation, it's going to take a lot of energy to undo that bond strength. I don't think I need much more here. I just want to look at the diagram. Good? Okay. So bond energy is the energy required to break a chemical bond. Again, this just kind of relates back to looking at it yesterday. Bond energy can really relate to thermal stability. I'm not worried about all of this. I guess there's an example, but do you guys have these diagrams in your book? No? I'm just going to talk through it, and then I'll tell you what I want you to write down. Okay, so an endothermic reaction. So remember, your delta H here is going to be positive, so that means that energy is required for this reaction to occur. And so it takes quite a bit of energy. So if we're looking at the decomposition of water, for example, here, it's going to take quite a bit of energy to break the bonds between hydrogen and oxygen. Why? Yeah, first of all, it's a covalent molecule, and then it has all these strong intermolecular forces. So it's going to take quite a bit of energy to break the bonds that are holding the hydrogen and the water together. And so in a endothermic reaction, the bond, you just want to write this down. In an endothermic reaction, the bond breaking energy is greater than the bond making. And again, if you were here yesterday, we did that little sheet. You had to answer that, and some people switch them around. So the bond breaking is greater than the bond making. So it takes a whole bunch of energy to break apart the hydrogen and oxygen, and then it takes less energy just to add the hydrogens and the oxygens together. And so overall, the energy change here is positive. It still requires more energy to break the bonds than it does to make the new substances. An exothermic reaction, then, is the opposite. So in this case, the energy required to break the bonds between hydrogen and chlorine is less than the energy that it takes to actually now take hydrogen and chlorine and add them together. And so my delta H is negative. So for an exothermic reaction, the bond breaking is less than the bond And so that's why we have a result of a negative enthalpy. Endothermic, yeah. Yeah, and this is exothermic. All right, so they always ask that question on, like, tests, diplomas, that kind of thing. Yeah, so make sure you know the difference. If you think about it in terms of a diagram, it should make sense. And that's just what I said. Okay, last thing really quick here is... Can't talk today. Catalysis? No. Catalysis. I can't talk. I'm not even trying. Okay. Catalysis. Deals with the properties of developing and making catalysts. And so obviously, this is just, I don't really know how much you want to write. Just kind of reiterating what we talked about earlier. Just looking at some real world examples of it. So a catalyst, obviously, they reduce the quantity of energy required to start a reaction, and they have a greater yield. Talked about that. I just want to look at just a big thing to note here is they don't alter the enthalpy change, right? If I look at this in terms of my energy diagram, if this is my reactants and this is my products, and you know, this right here is the pathway I follow with a catalyst, let's assume. My enthalpy is still only in this range, right? That's the delta H. And so regardless if I use a catalyst or don't use a catalyst, it doesn't change the enthalpy of the system. So that's a big thing to make sure that you know. Catalysts in real life, anybody know? Okay, probably most of you use it every day, but you don't even know it's there. Okay, sorry, you drive. It's something in your car. HSO4. Oh, in a esterification reaction, yeah. Yeah. Okay, so catalytic converter in your vehicle, which are mandatory, please do not be. They just speed up the combustion rate, and they also reduce the amount of bad, what do you call it, greenhouse gases being put into the atmosphere. They also allow us to use lower temperatures, reduces energy consumption, and also decreases those unwanted side reactions. Good thing to know. Everybody should know all of this. Good. And so we just talked about some of this. So in the oil industry, cracking, we're going to have a lot of catalysts. So remember when we were doing everything, and then they always write over top of, so here's my reactants, here's my products. They'll always tell you what your catalyst is over top of the reaction, if there is one being used. And that's where we've seen like HSO4 or light or bromine or whatever it is. And again, catalysts used a lot in terms of the relating back to that organic chemistry unit. Okay, so homework 5.2 and 5.3. Yeah, everybody knows what I'm talking about. Just relating back to bond energy and activation energy. I do want to, let me see. Okay, so just I want to point something out here really quick. Okay, so just sorry. You have to be able to label these diagrams accordingly. And so at the top here would be what?
The total energy.
Just at the very top is the activated complex. The difference between the products and the reactants here is what? The change in enthalpy. The difference between the energy in the reactants and all the way to the top where the activated complex is like initiated is called the activation energy. Okay, so you have to be able to kind of go in and label all of those parts in a diagram, whether it's exothermic or endothermic. Okay, so homework 5.1, 5.2.